This is the video to go along with the Piecewise functions homework, so make sure you've got that in front of you now so you're ready to make annotations whilst you're watching a video. A piecewise function is a function that's defined by different equations depending on what the domain states. So in this case we can see that f of x is 5 minus 2x when x is less than 1, and when x is 1 or greater, it's equal to x squared plus 3. So it has different rules depending on what the x values are. Part A says to sketch f of x. So let me start with when x is less than 1. Let me draw the 5 minus 2x. So that's got a y-intercept of 5. It's got a gradient of minus 2. So that's going to be a straight line like this. So that's the graph of 5 minus 2x, but I've drawn that across the whole graph, which I shouldn't have done, because the 5 minus 2x is only valid for when x is less than 1. So actually, it shouldn't be down here. And when I get to where x is equal to 1, so when x is equal to 1 here, to signify that the straight line won't be valid when x is 1, I'm going to draw a little hollow circle there, because my straight line is not valid for when x is equal to 1. It's valid for when x is less than 1, so all of this is absolutely fine. But equal to 1, no, and it's not valid over there for when x is greater than 1. For those values, we're looking at the quadratic, x squared plus 3. So let's think about that. Different ways we can plot this. Simplest way is probably just to do substitute some numbers. So when x is 1, 1 squared plus 3 would be 4. And I'm drawing a solid circle here because x can equal 1 for the quadratic. When x is 2, we'd have 2 squared plus 3, which is 7. When x is 3, we'd have 3 squared plus 3, which would be 12, and so on. So my quadratic is going to look something like this. And there we go, that's f of x. I've sketched it. Part B says to state the range of f of x. Remember, range is the y values. So I'm looking at the smallest y value here, and I can see it's 3. It can't equal 3 because that was the hollow circle there. But it could be anything as low as 3. So f of x has to be greater than 3, can't equal it. In terms of upper limit, I can see y is going to get bigger and bigger and bigger over here. It's going to get bigger and bigger and bigger over here. There's no upper limit to what y can be. So I'm just going to say that f of x is greater than 3. Part C. Solve f of x is equal to 12. So where is my graph equal to 12? Here's 12 on my y-axis. I can see it's going to equal 12 here and here. So let's find the x value for the straight line first. When does my straight line, the 5 minus 2x, equal 12? So subtract the 5 from both sides and divide both sides by negative 2. And x is minus 3.5, which makes sense from my sketch. What about the quadratic there then? Let's work out that value. It looks like it's 3 from my graph, but that was just a sketch. So let me solve this algebraically as well to be absolutely sure. So when does my quadratic x squared plus 3 equal 12? subtract 3 from both sides, and we get x squared equals 9. Square root, and I get either 3 or minus 3. But I am going to ignore the minus 3 because I know that in this case my quadratic is only defined for values of x greater than 1. It's not defined for when x is minus 3. If x was minus 3, I would be using the straight line, not the quadratic. So I'm going to ignore the minus 3 solution, and therefore the only two solutions are 3 and minus 3.5. Those are the two values of x where f of x is equal to 12. Part D then asks to solve f of x is greater than 12. Well, I can see that it's greater than 12 over here and over here. These values of x are greater than 3. These values of x down here are less than minus 3.5. And I could leave my answer as those two inequalities, or if I wanted to, I could combine them together in set notation to say it's a set of values of x such that x is less than minus 3.5, or the set of values of x such that x is greater than 3. So that's what a piecewise function is and how we can solve some problems with them. Let's have a look at a second example now, where this time we're given the graph and we need to be able to define it. So we need to find the equations and the domains for each section of this graph. I can see the purple part is a straight line, and I can see that that straight line has a domain from minus 4 for x is less than minus 4. I can see that the quadratic, the blue line, has a domain between minus 4 and 1. Now, that minus 4 point there, notice that the minus 4, 8 coordinate there, both the purple line and the blue line both go through that point. Therefore, I can include the minus 4 in the domain of the purple line or the blue line. It doesn't matter, you can choose which you're going to do. Similarly, the point where x is 1 and the y coordinate is 3, the quadratic goes through that point and the green line also goes through that point, so I could include the 1 in the domain of either of those. It's up to me to choose. So, f of x. I'm going to use the curly brackets here to group together all the different equations. Like I say, the purple line, I'm going to say that the domain for that is x is less than or equal to minus 4. I'll include the minus 4 with the purple line. Then I'll work out the quadratic that's going to be when x is greater than 4 but less than 1. I'll include the 1 there. And then the green line will be for where x is greater than 1. Right, let's work out the equations for each part here then. Well, the green line there, hopefully that's nice and simple. You can see that that's always just equal to 3. The quadratic, let's do that now. I can see that the quadratic has a root at 0 and a root at minus 2. So that's making me think that I could have something that looks like this. This is giving me the root of minus 2. This is giving me the root of 0. But I do need to be a little bit careful because there could be a coefficient at the front there that I need to find. So let's check another point that's on this graph just to work out what that a value is. let's check this point -1, -1. So when x is -1, y is -1. So let's substitute that in. The -1 plus 2 is 1. The -1, the a times -1 times 1 is -a. So a is just 1. So the equation of my quadratic then is just going to be 1 times x plus 2. And then finally, the purple part of this graph, that's a straight line. So I'm thinking y equals mx plus c. Let's pick 2 points that we can read off easily. Let's pick those 2 points. This is the coordinate -6, 9. And this is the coordinate -4, 8. So change in y, divide by change in x. We get -1/2. So my gradient is -1/2. Substituting the coordinate in to work out what c is going to be. So y is 8 when x is -4. -1/2 times -4 is -2. It's 2, sorry. So c is 6. Therefore, the equation of the purple line is -1/2x plus 6. And we have managed to define the function. It's equal to -1/2x plus 6 if x is less than -4 or equal to -4, because I decided to include the -4 as part of that. It's equal to the quadratic, the x times x plus 2, if x has the values between -4 and 1. Or it's equal to 3 if x is greater than 1. Like I say, if you wanted to, you could, instead of putting that there, you could have put it here. And if you wanted to, instead of putting that here, you could have put it here. It's up to you, as long as you include the -4 and the 1 somewhere, because they both have the same y values at those points.